Welcome to the video lecture. As a part of electrical machines, today I am deriving the EMF equation of single phase transformer. Derivation of EMF equation of a single phase transformer. Transformer is a static device. It has two main parts. One is the iron core, another one is the windings. It have two windings, one core. The main function of transformer is it transfer the power from one circuit to another circuit without change of frequency, but it either step up or step down the voltage. Okay. For understanding, just I am taking here simple transformer. So in this limb I am providing one winding, in second limb I am providing another winding. Once it is the primary which is connected to the voltage, AC voltage, that winding is called as a primary winding, which is connected to the load, that is called as a secondary winding. Once you give the AC voltage here, maybe primary side, it is denoted to the suffix 1, supply voltage, it draws some current I naught. Now the primary winding having N1 number of turns, secondary winding having the N2 number of turns. Once you excited, it set up the magnetic flux. This is called as a flux some instant. Okay, in this derivation, just I have to use so many parameters. Let us first we have to denote this. Here flux is nothing but instantaneous value, flux in Webers, and V1 and V2 is generally called as both V2 primary and secondary voltages in volts. So these are the instantaneous values, and we have to refer the actually effective values V1 and V2, vice versa primary and secondary voltages in volts. So in voltages generally this is called as a terminal voltages, but we are E1 and E2 another terms induced voltages in both side voltages, both sides, it is also measured in volts, but this is called instantaneous values. Similarly effective values also we are considering here. E1 comma E2 is called as the induced voltages in both side in volts. Here E1 and E2 is the instantaneous values, E1 and E2 is called as effective values, and also here main the number of turns N1 is treated as number of turns of primary winding, N2 the number of turns of secondary winding in turns, and another term here using the frequency of the supply in hertz. Okay, these are the terms here used in this derivation. Yeah, once you give the supply here, in this coil, primary coil, it passes the current, maybe under no load condition it is called I naught. So in this condition, maybe we have to provide the switch here, maybe under no load condition, how it is developed the voltage. First of all I explain. So according to Faraday's law, whenever a conductor or links with the rate of change of flux, EMF is induced. So here we are giving the a sinusoidal voltage with some frequency hertz, and automatically it passes the sinusoidal current, alternating current. Alternating current causes it set up the alternating flux. Alternating flux is linked with the both coils. So according to, so it have the same frequency, both I and F also, every parameters having the same frequency. Now according to Faraday's law, whenever a conductor links with the rate of change of flux, here it develops some voltage that is called as E1, E1 here is proportional to d pi by dt. It is the equation 1. Similarly, the second coil is also develop some voltage d pi by proportional to same flux. That's why it is proportional rate of change of flux. So here also some voltage will be developed, that is called as E2. Now but actually here the overall the answer E1 is equal to but that voltage proportional to d pi by dt, but it is equal to n number of turns in the primary winding. So it is the primary, you have n number of turns, n1 d pi by dt. But according to Lenz's law, that voltage is opposes, that's why we treat it as the minus n1. So this is the equation 3. Now equation it's not required. Okay, maybe equation 3. Similarly, E4 is equal to minus n2 d pi by dt. The equation 4. You know that actually here the pi is also instantaneous value. So it is a sinusoidal nature, we can consider as this one, pi is equal to here. Why? Because once you give the voltage here V1 it causes it causes the passes through the current. Now it set up the magnet that pi is equal to pi m sin omega t. This is the equation 5. So this value is substituted in equation 1. We can get it that E1 value, E1 is equal to minus n1 d by dt of what is the value, pi m. Here pi is equal to, the value is pi m sin omega t, pi m sin omega t. So we can differentiate this minus n1 pi m sin omega t is nothing but cos omega t into, we have to derive this derivatives, this is the omega. So overall answer minus n1 pi m omega cos omega t. So omega is nothing but it is angular frequency, that value is nothing but 2 pi f. Here we can substitute that value minus n1 pi m, replace this value, we can substitute 2 pi f cos omega t. Yeah, so in this one actually we are taking the reference is this equation. Why? Because here applies at the voltage sin omega t. So the voltage also you can write it in terms of sinusoidal nature. Rewrite as this equation n1 pi m 2 pi f cos omega t is nothing but sin pi by 2 minus omega t. So this minus is put into the inside of the sign, we can get it this one, n1 pi m 2 pi f sine omega t minus pi by 2. So it is also a sinusoidal equation. Entire this we are observed here, this is the one of the all fixed value, physical values, we are applied n1 number of turns, constant flux, and frequency is applied, applied frequency is a constant, entire this is a term is a constant. So any sinusoidal equation, it is called, treated as we can write it this one, Em, where it is the peak value instant, E1 is equal to Em. So we are writing for the primary side, that's why 1 Em1 sine omega t minus pi by 2. So from this equation, we observe that Em1 is equal to n1 pi m 2 pi f. So any AC quantities are generally in the nameplate details are otherwise measured in RMS values, that is called as effective values. That's why we are calculated the effective voltage. That effective voltage induced in the primary side is equal to E1 is equal to Em1 by root 2, Em1 by root 2. So we can simplify this, n1 pi m 2 pi f by root 2, we are getting as root 2, that equal to root 2 pi f pi m and n1. So root into 5, we are getting 1.1 this is we are getting this equation, simplify this, the numerical 4.44 frequency and flux and n1 turns. This is the primary side voltage. Finally we are getting E1 is equal to 4.44 frequency, flux and n1 number of turns. Similarly, we are applying the secondary side. Secondary side also it having the same flux and same frequency, but it simply change the number of turns only. We are using here here the U2 is equal to minus n2 by d pi. Same flux is substitute. Only 3 and 4 equation we are changing the number of turns only. Because of that, we are getting here. Similarly, we are derive the secondary side voltage also. We are getting this equation 4.44 frequency and pi m and n2. Maybe we are call it as these are the equations the 5. So this is maybe are call it as equation 6 and 7. From equation 6 and 7, we observed that per turn voltage, we are calculating per turn voltage from equation 6. So what you are getting, E1 by N1 from equation 6, we are writing this, E1 by N1 is equal to 4.44 frequency and magnetic flux. Similarly, from equation 7, we read it as E2 by N2 per turn voltage in secondary and 4.44 frequency and magnetic flux. So maybe these are equations called as 8 and 9. So we observed that from either in primary side or secondary side, the induced voltage per turn value is equal to 4.44 and frequency and magnetics. This is the quantity. So we observed that, so number of turns maybe in the secondary compared to the primary, the secondary number of turns are more. Maybe the transformer react as a step up transformer. Suppose if the compared to the primary winding, the secondary number of turns of the winding is less, it is act as a step down transformer. So it is act as a step down transformer. From these two equations, we are observe that E1 per turn voltage both primary side and secondary side is same. So that's why you can compare the voltage ratio. Maybe E1 by E2 is equal to, we are applying N1 by N2. This is called transformer ratio N1 by N2. This is denoted by A. This is very very important for finding the equivalent circuit of single phase transformer and calculating the remaining parameters in the transformer. So this is one of the example, but in transformer, in this transformer uh, uh, yeah, so it according to law of conservation of energy, energy neither be created or not destroyed. So that's why what power is given to the primary side, the same power is transferred in the secondary per ideal condition approximate. So that's why transformer having the very high efficiency, almost the 98-99%. So that's why their drop is also very less. That's why their applied voltage or terminal voltage are approximately equal to their induced voltages. Our terminal voltage here the E1 is approximately is equal to V1, and it is secondary terminal voltage approximately equal to V2. So that's why we are we can translate under this ratio any winding ratios, we can write it as V1 by V2 is also. We are calculating the values from induced voltage or number of turns, we can rewrite as like this equation N1 by N2 and A. Another important point, the same transformer, in the transformer power is same on both sides, or rather transfer the power from one circuit to another circuit. So meanwhile the losses maybe a ideal condition we are consider, that is equation apparent power in the primary side V1 I1 is equal to V2 I2. So by using this equation we are calculating V1 by V2 is equal to what is the value, V1 by V2 is equal to I2 by I1. So this is the another representation. Finally the A value is equal to, we can write it in this different voltages, either ratio of terminal voltages or otherwise ratio of induced voltages, or we can write it as ratio or otherwise N1 by N2, or maybe it is called in terms of currents, we can write it the I2 by I1. So this is the value of the A. So I conclude that transformer is a static device. It transfers the power from one circuit to another circuit without change of frequency, but according to Faraday's law, in both windings induced voltages are induced, that value is equal to maybe here E1 is equal to 4.44 and frequency and phi m into N1. Similarly secondary side induced voltage equal to 4.44 pi and frequency into pi m into N2. So from this equation we are calculating the per turn voltage. We observed that per turn voltage in both sides is equal to same. That's why maybe compared to the primary winding, secondary number of turns are more, it is act as a step up transformer, or compared to primary turns, secondary turns are less, that is called as a step down transformer. Thank you.